And now to take us home, Eric is going to talk to us about total type error localization and recovery with holes.
Yep, thanks. Everyone hear me? Good. Yeah, thanks for the introduction. So I'm Eric, an undergraduate at the University of Michigan. This is work in collaboration with folks there at the Future Programming Lab. Thanks for bearing with me on this last talk of the day. Though maybe it's on a sleepy Friday afternoon like this that we're in need of a reality check. And the reality is that most of the code we type is ill-typed. In fact, most of the time we start writing out the thing, so it's probably very ill-typed indeed. Or think about that time you spent, you changed some important function definition or type definition and had to spend the next several hours or even days fixing the rest of your code. So in fact, these ill-typed states can persist for a surprisingly long time. And for these reasons, we hope, or rather expect, our editor services and tooling to be able to cope with our ill-typed code. In particular, it means we expect them to, first of all, localize type errors, or tell us what and where they are in our code. And also, even in the face of them, sort of recover optimistically, continue doing whatever it's doing and find potential other errors, ideally with minimal loss in service. Code completion, for example, shouldn't suddenly be unavailable because I have a type error somewhere. And so naturally, this problem has garnered plenty of practical interest. And we can see that production tooling supports some level of localization and recovery capability. Let's look, for example, at this program that has f that takes a Boolean, x determined by a conditional, and then f applied to x. We can immediately see that the branches of the conditional are mismatched with respect to typing. So there should be some sort of error diagnostic. And in fact, if we threw this at the OCaml compiler, it would say, yes, there is, and it's on false, having sort of assumed the first branch to be correct. And so OCaml C will stop here, but the OCaml language server, which probably most people use in editors nowadays, will go on to say that there is actually another error on the usage of x, because it's determined x already to be an int, but f takes a Boolean. OK, this is all well and good, but what about Haskell? Perhaps someone unexpectedly localizes the error to 5, saying it's not an instance of num bool. This is presumably has something to do with how type inference works for the num type class. Rust is a little different in that it prioritizes the first branch like OCaml, but also suggests that perhaps 5 is to blame in all of this. And then Hazel, the programming environment that our group is developing, is yet different, assigning the error to the entire conditional. And the cursor inspector down here tells us that the branches have inconsistent types. So obviously, all these languages have very different type systems, but from this sort of informal exercise, we can see that practical systems do support type error localization and recovery to some extent. But localization decisions can vary a lot, and often tools are trying to guess about user intention. Then to recover, they have to somehow operate with incomplete knowledge of the types at play. And together, this means that upstream localization decisions can greatly influence downstream ones, perhaps somewhat unexpectedly. And so we think, therefore, that this subject could benefit a lot from some rigorous treatment. But unfortunately, our current developments in theory don't really reflect this reality. Most of the code we write is ill-typed, but conventional language definitions are only concerned with the semantics of well-typed programs. This is made most obvious by the fact that our type systems look generally like some variation of this judgment form. And so the result is that if a type error appears anywhere, as far as the specification is concerned, the program is meaningless as a whole. And so we'd like a way to alleviate this by being able to create precise specifications for the typing semantics of ill-typed programs and localize and recover type errors along the way. And these type checker semantics should describe all well-typed and ill-typed programs. We'll call this notion totality, and it'll sort of guide us as we go along. So this paper is about, we've developed techniques to achieve total type error localization and recovery by sort of elegantly blending local and global type inference techniques. For the former, we present in a sort of tutorial style the marked lambda calculus, which is a judgmental framework for total type error localization and recovery for bidirectional type systems. We choose bidirectional type systems as our starting point because the sort of flow of typing data it creates is conducive, we think, to intuitive error localization. Then we'll describe type pool inference, which is about how to layer a global constraint-based inference system atop the marked lambda calculus in a way that allows us to neatly combine bidirectional and unification approaches for even better localization. So while these two paradigms have been thought of perhaps as opposing or alternative techniques, we'll hopefully see how they can actually complement each other. And hopefully you'll be able to see that these techniques are actually fairly general and hopefully applicable to what you're doing right now. So to start this short tutorial, we'll start with a small, gradually typed lambda calculus with a standard bidirectional type system in which synthesis corresponds to inferring the type of a term from its syntax, and analysis is checking a term against an expected type. And it's important to note that we have the unknown type here, but in fact, it's actually only necessary, as we'll see, for ill-typed programs, handling ill-typed programs only. And we require then only the static semantics of the gradually typed lambda calculus, so no runtime shenanigans going on here. In our standard bidirectional type system, we would probably have a rule that looks like this, incomplete one, for synthesizing the type of a variable occurrence. We can conclude, of course, that x synthesizes type tau if the pair is in context. So hopefully this is straightforward. But the question is, and this is where totality comes in, what if x isn't in scope? And so this causes problems if we were to try to implement this rule, which might look like this OCaml code for synthesis. The none case in the lookup corresponds exactly to being unable to fulfill the premise. And it's really not immediately obvious what we should do in this case. A common approach is to just throw an exception with a diagnostic and leave it to the caller to handle, or similarly by returning an error value. But in either case, we've sort of aborted the type checking process early at the first error, and this just isn't going to cut it for the 21st century. So at this point, we've successfully localized the error, but the question is, how can we actually recover? Given what I said earlier and the fact that this session is about gradual typing, you probably guessed it by now, but it's by using the unknown type. And so the idea is to augment this type checking process with marking, where we localize and report errors by adding these marks, which intuitively correspond to compiler diagnostics or sort of editor decorations, for example. And then we'll use the unknown type, which provides exactly the right mechanisms via consistency to recover in a principled manner. So we'll take the original syntax of the language and add the aforementioned error marks, which are given by these sort of fancy parentheses in red with a subscript. But it's important to note that these are just sort of symbolic representations of actual error messages, which we don't talk about too much. For now, we have added only one error mark, which denotes exactly that the variable is a free variable. So then we'll extend the original typing judgments into these marking judgments, where unmarked terms are marked into marked terms. And these are now the judgments that actually express the error localizing and recovering type checking process. And then the idea is that sort of downstream services, editor services dependent on type information, such as completion, will then be based on these typed marked terms. So thinking about the success and failure cases of this variable rule, we actually get two synthetic marking rules. In the success case, we don't need to mark any errors. Hopefully, this is straightforward. And then in the failure case, when x is not in the context, we'll need to mark x with an unknown, a free variable mark, and then synthesize the unknown type since we don't know anything about it, naturally. Another common error occurs when some term's type doesn't match the one that's expected. In a bidirectional system, this commonly occurs when we have some sort of subsumption principle that we want to apply. And we can straightforwardly sort of derive a corresponding analytic marking rule. But again, totality guiding us here, the question is, well, what if the types are inconsistent, like in this example? And just as last time, we'll add a new mark denoting exactly this error. And then hopefully it's straightforward to see how we can derive the second rule on the right here that handles the error case. And again, we'll mark the term with that error mark. And so hopefully these two examples, though they're short, give you a sense of how this framework works. And if we were to continue the development for this minimal language, we would simply follow this pattern. And it turns out you would need this set of marks, which cover the remaining failure cases that would probably arise during type checking. And for the sake of time, I won't cover them, but you can see the full development in the paper. But now the question is, okay, with this development in place, we should be wondering, as researchers, how do we know the recipe? This sort of recipe has given us the right rules and that we haven't made any mistakes. From the start, I mentioned this notion of totality that would guide us. And now we can actually formally state it to make sure we haven't missed any rules. Here's the theorem, and it states simply that every unmarked expression can be marked synthetically and analytically. And of course, there's an accompanying theorem that requires that marking gives us only one result, as one would expect and hope. Secondly, marking shouldn't deform the syntax except by adding marks. And removing these marks, which is given by this sort of square superscript erasure operation, should give us back what we started with. And we should also have that marking shouldn't introduce any error marks on well-typed terms, because they're well-typed, which we give by this markless judgment. And then there will be a corresponding statement for ill-typed terms, which should have at least one mark. So putting these pieces together, we can view marking as a sort of total function, taking arbitrary terms, well-typed or not, of the unmarked syntax to well-typed terms of the marked syntax. That these are then used by downstream services. And this well-formedness theorem from the last slide is exactly described by this identity loop. And all this metatheory is mechanized in Agda, which can be found in our artifact. So the recipe that we've described is you can take your existing type system and formalize how type errors are localized and recovered from. You could start with a non-gradual system, but you'll need to add the unknown type, just the static portions to handle ill-typed programs. And then systematically, considering the success and failure cases, we can derive the marking rules, as we saw. And then it's important to know that all the decisions about how to actually localize were made by us during the process. And so this framework is not really prescriptive with respect to a specific strategy. And in fact, we actually, in the paper, just formalize the sort of three different possible ways to localize errors for inconsistent branches in a conditional, as we saw at the beginning. So since the marked lambda calculus is for bidirectional systems, it might not do everything we'd want it to. In this program, the type of f is given to be unknown, so the bidirectional system operates gradually, but we notice that, well, it's applied as a function, so maybe it's a function, but it's also being used as a number, so maybe it's a number. In other words, there's no way to sort of fill this unknown type or type hole, as we call it, with a known type that would satisfy all the constraints. And we think, well, some sort of global constraint-based inference system would have caught this error. And so the second part of this paper, we're talking about how we can layer constraint-based inference atop the marked lambda calculus to get sort of the best of both worlds, where the latter provides local type inference with error localization recovery. And then typal inference, as we call the system, solves and marks for these sorts of global inconsistencies. And it's important to note, rather than being a standalone type checker, this is an example of a downstream service that you would use with the marked lambda calculus. And so without getting into the weeds of how this all actually works, we can just, you can refer to the paper for details, but we'll just see how we can take the previous example into Hazel, where we've implemented this typal inference system. So this is what it looks like. And this is a constraint-based system, so we gather constraints and try to solve them with a unification algorithm. And when unification is able to solve the constraints, we'll proceed as normal to find the appropriate substitution. However, like here, when it's unsolvable, we'll sort of degrade gracefully to maintain these partial solutions, which are all the possible type fillings for the unknown type, which are then offered to the user for selection. And we can see here in this example that we have a red exclamation on sort of where the unknown type would be. That indicates that the constraints are inconsistent. And the cursor inspector tells us that they are and that they're int and int arrow unknown. So instead of failing outright, the inference system collects both these possible type hole fillings and presents them to the user, which we can actually preview by hovering over like this, and then select the one that we actually intend. So for example, when we hover over int, it fills int with a type hole, and now the application of f is marked with an error because actually control has now been returned to the bidirectional system. And likewise, if we hover over the other one, now the second usage of f is marked with an error. And so the nice thing about this approach is that it's neutral in the sense that we don't try to guess about user intent, but simply offer all the possibilities to the user for selection. And this facilitates a sort of workflow of filling in type holes and then returning control to the bidirectional system. And it turns out that these bidirectional and unification approaches can actually work together quite nicely. And so there's, of course, more in the paper. Please consider trying using these techniques in your next language, or tooling or editor support for your next language. And if nothing else, we hope this work spurs more work about the semantics of ill-typed programs. Thanks.
Okay, questions from the audience? Hi, Eric.
Hi.
So this kind of process, I think, was previously used in parsing, where it was discovered that like by manually encoding all of the incorrect paths, you can produce really good error messages for people, which is really great. But then it requires like the implementer of a parser to like write a lot of extra code, and people just generally don't like doing that. So I'm kind of like at a first approximation, it kind of seems like this more or less requires doubling the number of like judgment forms that you have to write in your language for your semantics. And if you have like a sufficiently complicated language, that could be like a lot. And I'm just curious if there's like maybe forward-thinking work about like figuring out how to like optimize or like choose specific things that you want to like focus on or like automate it or something. Chat GPT it, I don't know.
Yeah, I think hopefully it was evident that this recipe is really not complicated at all. And because of that, I think there's certainly possibility for some level of automation. But of course, the language designer or the tooling designer is going to have to decide how they actually want to localize these errors. And so there needs to be some sort of user input from that. Yeah, it's definitely true that you have to write a lot more rules, but hopefully you saw that the rules really mirror the original typing rules quite closely. So it's not like we're coming up with a whole new half of the system from scratch.
And hopefully worth it.
Yeah.
Hi, this is a really great work. It looks very clean. I'm really curious, why has this paper not been presented at POPL 20 years ago? Actually, I have a real question. What is the complexity, the added time complexity that your instrumentation adds compared with plain typing?
Sorry.
Do you have like results about how much time it takes to run your type checker as opposed to the like naive type checker?
We haven't done benchmarks of that sort, though.
I'm not talking about benchmarks. I'm like complexity. If you have some ideas about like the.
I mean, so it does, since
cost.
if you're referring to the marked lambda calculus, right? It's bidirectional, so it does the same bidirectional traversal that a traditional type checker would do. So I don't see any reason for it to be.
For example, if you collect the types of all the variables, maybe it's more costly. You need more data structures or to check things. I don't know. I'm asking if it's the same complexity or if it's going to be more.
I think it should be the same.
Yes, thanks.
Yeah.
Hey, very nice talk. Yeah, I think this is an interesting area. My advisor used to do work in, if you had ill-typed, like type inference constraints, kind of changing and removing types to try and suggest things that would unify. And there's like a lot of spaces of solutions in that context, but I don't know how many there are here. But along those lines, have you like thought about like, I don't know, machine learning or something else to kind of give recommendations of like, you may want to use this to kind of fill your holes?
So are you specifically, so I guess for the latter system, type hole inference, yeah, we've definitely looked at sort of the body of work that exists for that, and people have used various techniques and methodologies to determine how they should, like where they should localize inference errors to. We haven't, we're not so much, I guess the approach we've gone for is trying to be as neutral as possible. So we're not trying to guess where the user is intending by perhaps saying, oh, they use this sort of, this constraint appears more, so maybe that's what they intend. But simply offer all the possibilities to the user so that they can actually select what they intend.
Have you like put it in novice programmers' hands and seen if they got decision paralysis or anything?
We haven't yet, but yeah, we're hoping to actually incorporate this tooling for the class that we're teaching.
All right, thanks.
We're here. Have you considered adding, instead of making more type rules, adding slack variables to the unification equations that you derive, and then when the slack variables are filled, you can actually pinpoint the holes, the problems that there are in your code. So slack variables are an old, a bit of background. Unification is approximately generalization of Gaussian elimination on abstract trees, right? And in Gaussian elimination, you use it for optimization problems. And optimization problems typically use slack variables to turn inequations into equations. You can see an ill-type program as an inequation, and then add slack variables, and then the slack variables, when they fill up, as opposed to staying empty, point exactly to the same places. As the soft typing experience by Fagan and Wright, who based work on Didier Remy's record calculus.
Okay, yeah, I don't know too much about that. We haven't thought about that, but that sounds like it could be an interesting avenue.
And last question.
Hi.
Hi.
I'm kind of curious. Here in your marked lambda calculus, it's kind of a simple thing. You only need consistency. But I guess if you wanted to apply these kind of techniques to fancier type system, you'd need to gradualize them in some way. So you need to get the equivalence of consistency for whatever crazy relation your type system is using, right?
Yeah, so the sort of caveat of the marked lambda calculus is that, well, first of all, you need a bidirectional system. And second of all, you need these like gradual typing mechanisms. So, you know, if you had a sort of gradual version of whatever fancy type system you're thinking about, maybe a gradual dependent type system, like if you already have this type system, you can then, based on whatever constructs you have there and whatever rules there, you just need to consider sort of the failure cases and then derive the rules. So, yeah.
Thanks. That's very nice.
Okay, let's thank Eric.